So we've established that there's evidence of a difference in mean achievement across teaching techniques. What now? Remember, we had 4 techniques. And just because we've rejected the hypothesis that all the means are equal, that doesn't mean they're all different. Which ones are different from which? Maybe means teaching techniques 1, 2, and 3 are all about as good as each other, and it's just 4 that's different. Maybe 2, 3, and 4 are all the same, and 1's different, or something like that. So to look at that question, we want to start looking at individual means, making inferences about individual means, and in particular about mean differences. So you could start by making inferences about individual means. It's probably better to look at pairwise differences. But here's a formula that you can use to construct a confidence interval for each individual mean. It looks a lot like what you saw before back in week 5 when we did one sample inference when we first made confidence intervals. This looks a lot like that confidence interval. The key difference is that it's suggested here that instead of using the sample standard deviation in a group, instead of using SI, use mean squared error, square root of mean squared error, as your estimate of the standard deviation. And that estimate comes with n minus k degrees of freedom. So instead of having ni minus 1 degrees of freedom here, you'd have n minus k. Why would you do this? Why would you do that instead of just using SI? Well, if it is the case that our variances are equal, then this gives you a better estimate of the within group variability than just looking at the values in a group alone. So we only had 4 observations in group 4, for example. It's not easy to get an estimate of a standard deviation from 4 observations. We had 23 observations in total. If we can assume the variances are equal, we're going to get a better estimate of the samples of the standard deviation by using a pooled approach, using a pooled standard deviation, mean squared error. That term is estimated with 19 degrees of freedom across those 23 observations from 4 groups, whereas otherwise our group 4 standard deviation would be estimated with 3 degrees of freedom because we had 4 observations in that one group. So we get a much better estimate of the standard deviation under the assumption that the variances are equal if you use this approach. So looking at this formula, it's exactly like what we've seen before, except we replaced S with square root of mean squared error and changed the degrees of freedom accordingly from n minus 1 to n minus k. So we could do this for each group. We could construct a confidence interval for each group. You look at them, and yeah, look, mean for technique 4 seems to be bigger than the rest. Mean for group 3 seems to be less. I mean, there's no overlap between 3 and 4, so maybe they're different. But there's a bit of overlap with the others, so it's still not clear what's going on here. We still don't know for sure. And so to look specifically at which groups are different from which, we should use mean differences, just like we did back in week 8 with 2 sample t-tests. Let's look at mean differences. This is sometimes called pairwise comparisons. We're comparing pairs of means with each other. We can construct a confidence interval for the difference between mu I and mu j. What we've got here is exactly like the formula we saw in week 8 for confidence interval for mean difference, except we've got a different pooled estimator of the variance. Instead of using SP squared, which came with n1 plus n2 minus 2 degrees of freedom, we'll use mean squared error, which comes with n minus k degrees of freedom for the same reason I just mentioned. There's more information. If we're prepared to assume equal variances across all our groups, all k groups, we get an often much better estimate of the variance by doing this, and hence usually a narrower confidence interval.